So are there any questions from yesterday that you have dwelling over in your sleep? So let me go over a little bit what we did yesterday in terms of the laboratory and what Carrie did, I believe last night and early this morning to get you the data that we'll see this afternoon. I actually have protocols in here that so you kind of get a feeling of what was done behind the scenes, so you don't just kind of think, well, you know, here you go, here's your sample. I put in your binder, there's a one sheet of how we prepared these particular samples. It says preparation of epithelial and sperm cell mixtures. This is what, you didn't do this, but this was how the swabs were prepared for the class. And then there's another page that says LMD cell lysis, and this is the actual lysis protocol that was used. So you had collected your samples in a product called Lysin-Go. And if you look at this protocol, you'll see that all we did was add DTT to the sample, and we went through this incubation program of heating and cooling. So you actually do it in a thermocycler, and it's only about 20 minutes. And that's really designed to kind of just basically break open the cells. Does nothing to clean up the sample. And then there's another protocol that PCR set up for LMD samples, and this was the PCR that was performed. So it is a 50 microliter PCR reaction, but we did it for 34 cycles. And then finally, there's a page on the capillary electrophoresis. Everything is the same except I'll have to ask Carrie, when we prepared the CE, I guess it's different for the 3100 in terms of doing your high diformamide and your PCR product. She used, I guess, the standard conditions that they use. I can find out exactly what the mix was. But basically, it would be pretty much the same as you would expect most forensic labs to do. And then also in your binder, I included just a few articles that you might find interesting. There's one on sex-specific fluorescent labeling of cells for laser microdissection of DNA profiling. And there's also one that is kind of interesting about actually sampling products of conception to determine the father. And because, I don't know, in how many labs here actually get fetal tissue? And, would you say that it's often or just rare? Rare. But, it does happen. And I don't know, do you have usually who usually actually determines what is fetal tissue and what's maternal tissue? Do you have a outside person do it or an inside person?
The analyst.
The analyst, okay. And I assume, in my experience at least, for most analysts, it's pretty difficult to kind of see. And a lot of times, when I worked at LAPD, we actually tried to send it to the coroner's office to have one of the pathologists do it. And depending on the pathologist, some of them were very good at it and some not so good. So this was a way, I think with one of these articles, they actually did cryosections of the tissue and looked at the chronic villi to get the fetal tissue and laser dissect those out. So you just had fetal tissue. This is kind of interesting. There's also an article by Elliott. This was one of the first articles published regarding laser microdissection. They use laser capture microdissection, which is the Arcturus system. And there's my article in here also that was published in 2006. And there's also just a really short article on a group that did PCR on a single sperm cell using laser microdissection. There's just kind of interesting articles that relate to forensics.
You feel something to read on your things like that.
Yeah. Okay. All right. So today I'm going to start with talking about our research studies at Chicago Medical School, or now it's called Rosalind Franklin University of Medicine and Science, but it's a very long name. And how did we really start this? We talked about this a little on the first day when we did introductions, but I just wanted to kind of put this in the PowerPoint so you had the information of the history of how we got this started. In about 2003, that's when I looked into the applicability of laser microdissection for the use in forensic science. And it was actually part of my thesis topic at the time. And then it kind of exploded into what became a grant proposal for NIJ. And then myself and Dr. Peterson, we got the grant from NIJ, but that wasn't until actually 2004. But just before that, we presented a paper at AAFS regarding laser microdissection of our preliminary data. And then several presentations we made through it at professional meetings. And that was kind of when we I first met Kelly, and then Pat were interested in this laser microdissection. And then they got on the bandwagon and got their own instrument. And then here we are in 2007 at the Technology Transfer Workshop. And I'm hoping a second manuscript is in the works very soon. I showed this slide earlier on the different separation methods. So you've seen this. And so we have some different things. We have flow cytometry. You know about preferential lysis. The problem with things like flow cytometry right now is you usually need a lot of sample. That goes also for membrane filtration. Magnetic antibodies, the problem with that a lot of times is the persistence of the antigens on the cell surface, especially in degraded samples. And then microchip separation, there's a lot of work still being done on that, so that'll be kind of interesting to see where that goes with cell separation. And again, Y chromosome is a way of deciphering mixtures, but it's a non-physical separation. And so we were looking at laser microdissection. So we looked at several different studies in order to evaluate whether laser microdissection would be feasible for separation of sperm cells from an epithelial sperm mixture. So there's a lot of different studies, a lot of workup, even before we get to the point where we're thinking, can this separate a mixture? We have to determine, what about the staining that we use for these samples? How are they going to affect our downstream analysis? So we had to do a histology study. And then also, what kind of isolation procedure would be the best suited for these type of samples? And then this yield evaluation by qPCR, I'll go into it a little more detail later, but we wanted to see how much actual DNA we were getting when we were collecting these cells. Then, of course, the mixture separation study. And then we went into the low copy number study, which actually was one of the more exciting portions of the study. Then we compared the preferential lysis method with the laser microdissection method. And then finally, we had a couple of cases that we were able to get hold of and actually do laser microdissection on. So before I go into the studies, I just wanted to talk a little bit about technical obstacles. First, I want to kind of open it up. Were there any particular technical issues that you guys experienced yesterday that were of concern, or that you noticed would happen, or things like that? Was there? None. It worked perfectly. Well, actually, using the new instrument, I noticed that, and it's a lot of the technical issues that I may have had with the older instrument. I no longer had those issues. I don't know. I had in my group once, I had one hanging chad. And did anyone have did you talk about hanging chads?
Actually, we didn't have to talk about it because we had quite a few. I don't know if we just didn't have the power set well.
Okay.
We kind of messed around with the power, right? Power, I'm saying the right thing. Which helped, the little bit higher power helped, and sometimes slowing it down. Right?
Okay.
So we did have a few hanging chads, but it was good because then they kind of learned how to do the move and cut.
Right.
And
yeah, I think with this new instrument, if you have it set just right, you have very few hanging chads. Even with the older instrument, when I had the parameters set just right, I'd still have maybe 10% of the time of these hanging chads. And depending on the day, it seemed like I would have more hanging chads than another day. But if you notice, there's a lot of optimization that can be done with the instrument in terms of your power and your speed and things like that. And that's something that you're going to have to do if you actually get an instrument and start cutting samples, is you'll have to do lots of smears and see what are your optimal conditions in terms of cutting. And we didn't have a lot of time to play with that, but obviously you want to be able to cut as fast as you can, but you don't want to use, you know, you don't want to just blow your samples out and use too much laser power. So just keep that in mind.
Well, and you know, I have to say that I think really the biggest problem was we hadn't optimized our laser settings.
Okay.
And but at the same time, I actually was timing everybody because I wanted them to see how quick this went, especially with the new microscope. It's so fast. And even with the hanging chads and having to go back and cut them, I mean, a lot of these cuts were done in under 10 minutes.
Okay.
So I mean,
that's
it's still just
much faster.
Yeah.
Which is nice. Yeah, and if you'll notice, and in my group I talked about it, if you're cutting sperm cells that are just out in the middle of the film, it's very easy and you don't have to use much laser power. But if you're cutting it within a field of epithelial cells, you have to actually adjust some of the parameters to be able to cut through those cells. And the next thing was the microscope slides. And we talked about this, and you've seen them, the pen slides, and that they have architecture to them. Obviously, we're hoping that that's improving with some of these new slides that are coming out and the director slides. And we'll actually look at the director slides that you prepared yesterday. And then there's also environmental conditions of the instrument. Now, what do I mean by that? Now, I didn't have any problem yesterday, which I was really glad. What we found in Chicago, especially in really humid summers, when the humidity was very high, we would have problems. And also in the winter, when it's extremely dry, we would have problems. So in the dry winters, we'd have problems with static because, you know, you'd have these little pieces of film that perhaps you wanted to like stick to the underside when they would cut, things like that. And in the summer, when it was humid, I'd actually have more trouble cutting. I didn't know if my sample was absorbing more water and it was harder to cut. But what we ended up doing is that using a dehumidifier in the summer in that room and a humidifier in the winter in that room. And it was just one of those kind of those hardware store type units, nothing fancy. And now I know our conditions, ideal conditions were like 35 to 45% humidity in the room. You find that it was different, Kelly, right?
Of course, now I'm in Shreveport,
Louisiana, where it's fairly humid a lot of the time. You know, it's definitely probably more humid than Chicago. Although I don't know, summer might be different. But I found that 50 to 65% was good for me. But now I think too a difference can be, I don't know what kind of room you have yours in, and I think if you were to get, let's say, the Leica microscope, I'm sure Andy would, if he came to your lab, he'd say, you know, an ideal room would be, I think, a smaller room, because now we have our microscope in a pretty small room, and it's actually in the basement, which is nice. It keeps it a certain humidity. And but what's nice about that, if you have to use a humidifier or even a dehumidifier, the smaller the room, of course, the easier that will happen. So that's something you would want to consider is if you have a room in your lab or your building that you think might be better suited for at least the Leica, but probably even all the microscopes are similar. I mean, I think a smaller room is better, because initially we had our microscope in a large room, and I definitely had more issues with dryness or humidity. But I've found that the like 50 to 65% range really works for us. I'm not sure why, but.
Yeah, and I don't know if it's our hydrometer. Is it a hydrometer you use?
Hygrometer,
yeah.
I think.
Yeah, I don't know. Maybe mine wasn't so accurate, but
Maybe.
I don't know. We had ours in a small room, and which was nice because in the morning you can kind of check and then say, oh, I'm going to cut, so I better turn on the humidifier, dehumidifier, things like that, so it could run. The other thing is not just the instrument, but the sample itself of the slide. I found that a dry slide is the best. So that's why in the protocol, I would usually prepare the slide, I put it in a vacuum desiccator, and I dry it out. And in fact, even if I decide, say I prepare my samples one day, I'm going to cut the next day, and or even a week later, and I put them in the freezer. And of course, when I pull them out of the freezer, there's going to be condensation. And I would just pop them in the vacuum desiccator for 20 minutes before I would cut. And I found that was good. So dry sample, but not too dry of a room. It's kind of this balance. You don't want static, but you don't want your sample to be wet.
Christine, I want to add to that.
Yeah.
He said this is true for any of the systems that are out there. I mean,
Okay.
every system has their environmental factors that are careful about. Some manufacturers are a little different. It's just that what Christine says is the last part is the sample being dried is probably universal. All samples keep them dry. But the environment is always going to be an issue.
Okay, I wasn't sure about that. I was going to ask you.
It's pretty universal for all machines.
We just talked about hanging chads, and you saw them. And with the new software, it's with the hold and cut feature. It's very nice. You can pop those hanging chads out if you need to. But I talked about static if it's too dry in the room, and then there's a collection buffer. With our protocol, now you have the option of using the sort of small PCR tubes, which are the 0.2 and or the 0.5. Now I always use the 0.2. But the cap obviously has a much smaller volume that it can hold. I think in the reality, 30 microliters is probably the maximum amount of liquid you can put in that cap, and that's probably pushing it. So,
You want to put 30 in that.
no, I'm thinking that it's probably going to overflow.
Okay, now is that pertaining to these particular tubes?
These PCR, so
Because
you have
our
round
tubes
dome.
are different. We have a round dome.
Okay.
Of course, Mike was nice enough to make us a custom tube holder for our old microscope. Now, I don't know if they could do that with a newer microscope, but I actually use it, and I'll get into this more, but I use a 50 microliter buffer catcher, when I'm cutting.
Okay, so that's a good thing to know, and I didn't really think about that with the flat tops. 30 is too much. I think 25 is really the max, and I had you folks put in about 22, and that was usually the working volume. If you want a larger volume, you're going to have to think of something like that using a different type of tube, or go to the 0.5.
The 30 and the 0.5 tube actually works pretty good in the flat bottoms. 0.5. So I understand you get a transfer to a 0.2 eventually.
Yeah.
But
See, that was my
Yeah,
issue with Andy. He kept saying, 0.5s are better, but I said, well, but we really like just doing everything in that PCR
Yeah,
tube.
exactly.
So,
So something to be aware of too is if it takes you a long time to collect a sample, and you only have about 20 microliters in there, that's going to evaporate, especially again if your room is too dry. So when you're collecting, plan on putting your buffer in there and collecting your sample right away. Don't think like, I can collect 100 samples, walk away for a while, and come back, things like that, because it will dry out. I mean, you're also under a microscope, and there is light coming through, so there's slight warmth there also. Okay. Were there any technical issues that you wanted to bring up? You thought that I didn't.
no, I
that
think
maybe you experienced.
You hit on all of them.
Okay.
I think that I don't know about the whole moisture thing. If it has to do with if the director's slides, if it would make as much of a difference. Because I know with the pen slides, what happens if there's moisture there, it will actually bubble up under the film.
Yes.
So you get these bubbles in your slide. Now, we actually, believe it or not, I don't do any type of vacuum desiccator. Generally, I just do the staining and with the ethanol, kind of let it dry. But I think that's probably still something we'll have anyway come casework, is just have a vacuum desiccator to make sure that those slides are nice and dry. But I don't know if the director's slides would have the same kind of issue.
Right, they may not. They may not, because they're not.
there's two issues here. Okay, let's talk about the membrane slides, because remember the film is attached to the glass slide, and if you are really rough with the membrane, you will have leakage. Okay, that's a fact of life. And I want to tell you up front right now, if you have leakage, the slide is still usable. You put it in a vacuum desiccator, and it'll dry out eventually. But you can't cut if there's a bubble behind it. Just don't even bother. Don't even bother. It's pretty true for any of the systems. As far as addressing the director slides, we all know that are new. These environmental factors need to be tested also. Okay, they're going to be an issue, because bear in mind they're going to be even smaller particles that are being forced into the cap. So I'd just be concerned about that too.
Okay.
I had a question about
go ahead.
the cap part of it. It seemed like it was, I mean, you may be more proficient as you work with it, but it did seem a little difficult to take the tube out and close it without having a possible oops.
Yeah.
My question is, I know, I'm assuming because you can visualize stuff on the cap, we kind of discussed it when you cut it, and it would probably be more difficult if you actually had stuff dropping into the tube directly, but is that something you've considered, or have thought maybe an easier way to come up with something? Because I mean, I can see if you're working on a very limited case with, this is all you have, and then oops, that's not going to sit well with management, or the papers or news or something. So
The comment is that, yes, you have a very precious sample, okay, and the issue is that is there easier ways to get the material out of the cap or get the cap out of the machine? I can refer to the fact that there was a comment that you can use sticky caps, which obviously there's nothing going to spill, but then that sort of defeats the whole purpose of the time. So it's not that we can't use a cap that has a sticky substance to it, because many other manufacturers use a sticky cap substance. We can do that. The problem is that then you're not taking advantage of having the material drop directly into your first glycate buffer, saving a tremendous amount of time. So understand that you're pushing the whole process here by taking advantage of the design concepts of our machine, that you drop it directly into. If you feel that 5 sperm or whatever your low copy is going to be very important, and you rather not do that, you can drop it into a sticky cap, but then you have to transfer. Now there are other, your comments are not the first about how difficult the cap is sometimes to get out. Practice does make it easier. That's a good comment we'll take back to the factory and see what they can say, that whether they can make it easier.
I think I could put a little different perspective on that. From a case working standpoint, I completely understand what you're saying, because every time, because of the old model, it's actually much harder to get that tube out because there's no back plate, that silver back plate. We don't have that. It's just empty space. So I'm always kind of nervous when I'm taking that off. But just to put it in perspective, yesterday, most of you had 3 spots. They were all 3 microliters, and usually you have a tube that you've done your cellular extraction, like in PBS. And most of the time we leave, like, let's say 50, 75 microliters in there, right? So the way Christine had you made yours yesterday, you only use, let's say, 9 microliters. So number one, you still have, as a laboratory, you could always keep that tube, freeze it. Let's say you just had to do a regular extraction. Come like the worst scenario, you might be able to go back to that pellet. Okay, so that's one thing. Number two, as most of you saw yesterday, at least I tried to point out to you that we're at my microscope, I said, now look, what you've cut, you've only cut from one of these spots. And if you have a good sample, and even a sample that really doesn't seem like it has a whole lot of sperm, once you put that many spots on your slide, or if you put a larger spot on your slide, you're going to be surprised how many sperm are there. If you have sperm, usually there's enough to work with. So as far as the 5 sperm scenario, yes, if you're only cutting 5 sperm, that's a very precious sample, but chances are you have more to go back to. And another issue you could come up with in your laboratory, you could say, okay, we're not just going to cut 1 tube, we're going to cut 2 or 3 tubes of this, so that way, if something were to happen to one of those tubes, or let's say the analysis didn't work on that 1 tube, you'd have these other 2 cuts that you've done, or you could do them all together, like 3, like triplicates or whatever. So that, I don't know if that helps kind of get you thinking, but.
Also, Annie's right in that after you do it a while, you get pretty proficient at it. I think after we were just rolling out samples, maybe a couple of times we lost sample because we weren't careful out of the hundreds that we did. But yeah, it's something that you're right. It'd be nice if maybe it was a little better designed, I think.
One more thing, if you're trying to alter your light path in the microscopy,
if you flip that tube and try to drop it into the tube, you're going to have a pretty profound effect on the light path going up to that tube, as opposed to that very small cap, which is in our case is rounded or flat. But if you try to drop it into a tube where the light path is being affected by that long tube, you might have some other issues with that you don't have with just the cap.
I think you would have increased static issues also, because one thing that there was an engineer that came to our lab at one point and took apart our microscope and cleaned it, and I was kind of talking to him about the static, and he explained to me that the more plastic that's exposed, plastic in general has a tendency to create a static charge. I think if you had liquid in the bottom of a tube, you're going to have a large amount of plastic, there, and I think the static issue would be maybe even more of an issue in that situation. So. I think the cap is a good idea, but yeah, as far as taking it off, that's a little tricky.
What kind of procedure do you need to use to take it off of a sticky cap? That's much more time consuming, or?
Well, most of my people drop directly into some kind of liquid buffer. But for some cases, they drop into the sticky cap. The sticky cap is basically the cap of a PCR tube. It's a special cap. Many manufacturers make this, and it's similar to what is it, Becky? It's like it's a gel or
Yeah, they don't tell us what it's actually made of.
it's a
It's
gel.
like a gel, yeah.
It's a gel, and do you use that, Becky?
We've tried it, yeah. So we've tried catapulting it into the sticky cap. So we actually then take a scalpel and remove that sticky substance from the
You
cap,
actually use a scalpel.
and then use it as kind of treating it as a substrate. So we drop it into a 1.5 and then
Okay.
did the extraction. Now, that's not something we decided to stay with, but that's just how we tried it with the sticky caps.
It's much labor intensive.
Right, and they also recommended, you could probably do the whole extraction with the tube upside down, which kind of freaked me out a little bit.
You shake it and
Yeah, but actually performing the extraction with the tube upside down so that you have the extraction buffer right on top of the sticky cap, then flipping it. And
My
I
only
decided I
concern
didn't
about
like
those
it.
sticky caps is the fact, are they going to be pure?
right,
That's my concern.
exactly.
and can you autoclave that?
Exactly.
Yeah,
Which is exactly why we ended
You
up
can't
not going
autoclave
with
the
it.
sticky caps.
I don't know whether
They-
you can autoclave
They
those
don't
sticky caps.
recommend it.
Okay.
Right, but it's something that they've taken back to try to troubleshoot. But yeah, we decided not to go with it.
All right. So the first study that I'll talk about is the histology study. And so what was our considerations to that? We wanted to visually discriminate sperm cells and epithelial cells, obviously, and then determine what the effect would be on the downstream analysis. And these are photographs of unstained samples of sperm and epithelial cells. And I actually did try to do some cuttings of mixtures of these samples. And although you could do it, and remember the samples I had were a little more clinical type, so they were not, probably had more sperm with tails, and epithelial cells were nice looking, things like that. So it's easier to identify. But I noticed that when I cut unstained cells, it took longer, because it took me longer to identify, and then also there were some samples that I still got mixtures, like maybe I didn't see that epithelial cell nuclei right by the sperm cell. So you really have to stain the sample, at least the way with the pen slides right now. So we actually did this in two parts, because the first staining set we did, and then we thought we needed to do more stains. So the first staining set we looked at, hematoxylin eosin, or H&E. And that's a very common stain and used in pathology. And I think in the UK, you would expect them to use H&E for sperm identification. Then we also looked at Christmas tree stain, or nuclear fast red, and pico indigo carmine, which most labs here in the US use for sperm ID. We also just looked at some of these other ones that maybe there was some literature on. Acridine orange had been looked at for sperm ID. Right stain is used for a lot of blood smears, so we looked at that, and with that possibility of using it on blood stains. And then also methyl green, which is a nuclear stain. And then we evaluated them for their ability to ID sperm. And then we collected cells from samples that were prepared and stained with these stains, and isolated with a QIAGEN-QIAMP. And because this was an earlier study, we hadn't done the Lysengo yet, and we did a QIAGEN-QIAMP system. And then profiler plus amplification was performed. These are some examples of some of the stains. You have acridine orange on the left, non-stained, Christmas tree stain, and hematoxylin eosin. And I didn't show right stain, because right stain, for whatever reason, I don't know the exact chemistry behind it, but it actually caused some kind of deformity in the membrane. It would pull at it or something. I don't know what would happen, but right stain did not work, and also even in the cells, it seemed to deform the cells in some manner. And then methyl green, although it was a nice nuclear stain, it is a difficult stain to control in terms of the intensity. So it wasn't very consistent in its staining. So we pretty much eliminated right stain and methyl green right off the bat. And this is just kind of a general scoring that we did. And be aware, this is just one analyst doing this scoring. So we wanted to get a general idea, can we ID these stains with these samples under these stains? So in this chart on the top, you see the different stains, and we kind of rated them, pluses being good ID, and then minuses being poor ID. And you look that the CTS, Christmas tree stain, performed very well in ID, and H&E did pretty well too. Be aware, this was done by me, who 10 years of looking at Christmas tree stain. So there's a bias toward my experience in seeing sperm with Christmas tree stain. If I gave these same slides, I bet, to someone in the UK who had done 10 years of H&E staining, those scores would probably be flipped. So just to give you an idea that there's a bias in here, but I wanted to get an idea that we make sure that these stains I could ID the sperm. And I'm just going to look first at H&E and Christmas tree stain because those are the ones that perform the best. And we did Profiler Plus, and we basically determined the RFU level relative to unstained samples. So when we did this, remember, we're not doing mixtures yet. We're just doing sperm, a smear on a slide, and determining how these stains affect the downstream analysis. So you can see H&E on the left, the RFU values were about 62% less than unstained samples, also cut from a pen slide. And then the Christmas tree stain was about 43% less than unstained. So there was the stained specimen definitely exhibited RFU values significantly lower than unstained specimens. So okay, there's definitely effect there. And if you want to kind of think about, well, what is going on for people who are really chemistry buffs, does anyone have a thought, let's say on H&E, why we would have a reduced amount of product? And I wrote it down here to remind me. Actually, when I looked in the literature, somehow hematoxylin seems to resist digestion, and this affects the enzymatic replication. So that's what they're thinking is actually happening. Maybe the hematoxylin is affecting it. And then eosin is pretty acidic also, so you may have degradation of your DNA. And then if you look at Christmas tree stain, picric acid, that's pretty acidic, that you could be degrading your DNA. And then indigo carmine, obviously indigo is a known inhibitor, so that it's not surprising that we have lower RFU values. So let me go through all the stains. The methyl green and right stain weren't suitable for LMD. We knew that just visually. We did do some DNA work with that, but they were okay. But since we can't ID the specimen, they're no use. Cell stain with acridine orange. Okay, there was no PCR product at all from any of those samples. And I think acridine orange is actually a interchelator, so that probably explains why we didn't get any PCR product. Also, acridine orange, although the sperm were really bright, it also really fluoresced on those E cells. So when you had a lot of E cells, it was hard to find your sperm. So Christmas tree stain and hematoxylin and eosin. So they were good stains for sperm ID, but we got significantly lower RFU values than the unstained control. But despite the fact that we got lower RFU values, we still obtained results. So that's important. We got results. We were at the higher level here at 300 sperm cells or 150 E cells. We're working at high numbers at this point.
Did you compensate for that by increasing your injection time?
Not at this point in this study. We weren't going yet to try to increase our sensitivity until a little later. Because the whole point of this one was just to see if there was in fact an effect. So, okay, what did we do then? Then we thought, well, so at that time we saw, okay, H&E was our best choice. But then, let me go back. So these results prompted a second phase of the histology study. So we want to do a little more work to try to improve our results. And so we did an H&E modified test. And so that was a shorter exposure time. Instead of, I forget what the first ones are, I'll have to look it up. But the modified version was more like 5 minutes of hematoxylin and 30 seconds of eosin. Very quick. Then we also decided just to use nuclear fast red alone, because in literature that's been shown not to have any effect on downstream analysis. And in fact, that's what you used yesterday. We also experimented with some fluorescent stains at this point, cyber-14 and propidium iodide. Cyber-14, you should be able to see your sperm with the cyber-14. And then what you did yesterday in the fluorescence lab, and I tell you, I did not do any kind of optimization. This was just a quick test that we did in the lab. We worked on PSA and PI. And PSA is actually a P-lectin. And I apologize, I don't know a whole lot about it because we decided not to do a lot of research in this area. And the reason why you're doing it in the lab was we kind of had to do a last-minute change. And we did have this protocol, and I knew that you would probably get some results. But just so you know, that's the protocol that you used yesterday. Oh, and also the cyber-14 propidium iodide, it's actually a kit that's used a lot in fertility studies. And in fact, PSA-PI is also a stain that they use in fertility studies. The PSA is supposed to determine whether the acrosome membrane is intact. So the evaluation, we didn't do a full evaluation of the sperm ID. We just kind of looked at them to see, okay, can we see the sperm and ID them? But then we collected cells, but by this time we were using the Lysengo method. So we used Lysengo extraction at this point. And now you're wondering, okay, now I changed the extraction. Is that maybe that's the reason why I might get results or not get results? I have another extraction study to show you in a moment to compare Lysengo and the Qiagen extraction that I used. But in this study, we used Lysengo and did Profiler Plus. So looking at just unstained cells, the H&E modified protocol, and nuclear fast red. So on the left, we collected sets of 300 sperm, and there's actually no significant difference between any of the samples. So there's no effect. And then with epithelial cells, we did the same thing, and again, there's no significant difference in the RFU values we obtained. So this was great. We have stains now that have no apparent effect on the downstream analysis. We chose to use nuclear fast red, mostly because it was just simple and easy, because H&E is a slightly longer protocol, but it's just something, these are at least 2 stains that you can use. And I didn't mention it, I think if it's not in your binder, I'll make sure you get handouts. There's one page with a website that relates to all these studies on one of the NIJ reference websites. It's like about this thick, that's why I didn't print it up. And it has all these studies in detail, and the results, and also many of the protocols. So what was the summary of the second part? Oh, the propidium iodine we had done, and there were no results. Again, it's an interchelator, so that's probably the reason why we didn't get any PCR results. Propidium iodide, though, we had done a little test on that, and that didn't seem to affect DNA analysis. So something to consider if you're thinking about a counter stain in fluorescence that propidium iodide you might want to use. The H&E modified and nuclear fast red, both of them were great, and no significant difference in RFU values obtained from that of the unstained controls. And that FITSI, the PSA FITSI PI stain that you used, again, we didn't do a full-blown study on that. We just did some testing, and we didn't optimize it. But it seemed to have a good staining. But if you're thinking about going that direction, I don't know how it's going to work on degraded samples. I really don't. These are more fresh samples that I have. Oh, and this is an example. Oh, I wish it came out better, but on the screen it looks good. Let's see. I don't know if this will work because it's a dark slide. Yeah. Okay. So these are sperm here, and you'll actually see your slides. And this is on a pen film. So remember or not remember. I don't know if we've talked about this before. On a pen slide, that architecture of all these little dots you see in the background. Those are the pores, and that's one of the problems with fluorescence and the pen slides, and why we use the director slides for your samples that you'll see this afternoon. Thanks for turning the light on. So those are the sperm cells, and these are the epithelial cell nuclei. Okay, so going on to the DNA isolation study, what did we want out of this study? We wanted to kind of have a process that was low manipulation, because eventually we were thinking low copy number, small volume, and considering how pure of a sample do we need. And we looked at a few different products. We looked at Lysengo, which is a commercial license buffer, low manipulation. And it involves a series of heating and cooling incubations to lyse the cells. And there was also another product, microlysis, we used. Same situation where it was low manipulation, a series of incubations. And then the QIAGEN QIAMP, which is a commercial kit, and some forensic labs do use it routinely. And it involves DNA binding on a membrane column that you clean out your DNA. So you get a nice clean sample with QIAGEN QIAMP. Lysengo and microlysis, obviously you have no cleanup involved. And then Helix is a popular method. We did a few samples on Helix to see if it would work. The problem with Helix, we found, was because of the beads, and we wanted to work in a very small volume, it was hard to separate our actual extract from the beads in that low volume. And we didn't have much success at all in our DNA results using Helix. So we abandoned that pretty early on. But all of these products are pretty much used out of the kit, except we added DTT to lyse the sperm cells. So what we collected, we're still at this phase in our analysis, we're working with large amounts, 300 sperm cells or 150 epithelial cells. And if you look here, we did Profiler Plus, so we have 10 loci there possible. And if you look across here, first just at the sperm cells, you can see the QIAGEN in the black and the QIAGEN QIAMP Lysengo. We had full profiles with 300 sperm cells using those methods. But microlysis did not perform well at all. And with the epithelial cells, we had QIAGEN QIAMP performing very well. Lysengo seemed to be okay. And then microlysis again didn't perform very well. We have kind of you look at the error bars, there's kind of a wide error in the number of loci that were detected. So there's quite a bit of range there. So actually microlysis we determined was not appropriate for these types of samples, these types of cells. So that's why I have microlysis crossed out in here. If we just look at the PCR product detected instead of the number of loci, well, how much signal are we getting? If you look at this, is kind of interesting. You look at the buccal swabs and those cells. QIAGEN, we had much higher signal than the Lysengo. And in fact, there was a significant difference. So Lysengo is not an appropriate method to use if you're collecting epithelial cells. But if you look at the sperm cells, in fact, well, here it looks like Lysengo performed better. There is no significant difference between using either Lysengo or QIAGEN on sperm cells. So, well, why? And we replicated this. So, why are we getting poor results with Lysengo on epithelial cells? Can anyone think that what might be the reason? Our thought is that when we did the E-cell study, we didn't just collect the nuclei, first of all. We collected the entire cell. And with the sperm cell, we just collected the head. And perhaps with all the histological agents and maybe even just all the cellular components, using a Lysengo procedure for an epithelial cell just wasn't enough to, you still had all those components in the tube, and perhaps it inhibited PCR. So you need a little more cleanup if you're doing epithelial cells. With the sperm cells, perhaps they're very small. You're collecting a very small amount of material and maybe not carrying over all those components into your reaction. So you can see QIAGEN is very clean. It's clean. You get good results, and it is good for epithelial cells. But just keep in mind, we actually went, since this study was concentrating on sperm cells, we went with Lysengo at this point in our analysis because it's so quick and low manipulation. And that's what we wanted for our low copy number studies. QIAGEN, I don't know, have any of you used the QIAGEN QIAMP system? Yeah. I mean, first of all, it's costly. And you have to transfer the sample, things like that, and then you finally get a product. You get a pure product, but we didn't want that type of system for a low copy number. studies. Let's see. So, in summary, for the DNA isolation study, microlysis was not suitable for LMD with forensic STR analysis. And QIAGEN performed best for collection of stained epithelial cells. But both Lysengo and QIAMP perform well for isolating DNA from sperm cells. And you have to decide what maybe you want. And you might have another method that you want, because these are just considerations. Lysengo provides a very low manipulation method and is inexpensive. I don't know, I forget how much those bottles are, but it's not a tremendous amount, but you can see how little sample you use from that tube. You only use 20 microliters. That one bottle goes a long way. QIAMP provides a cleaner DNA extract, but higher manipulation, it is a higher cost. So then let's look at the DNA yield study. So the LMD process may provide an estimate of DNA quantity. Why? Because you know how you can count the number of cells you have. But the efficiency of the DNA extraction process has to be considered. And I didn't really find in the literature any studies on the commonly used extraction methods on true extraction efficiency. So we kind of wanted to take this into consideration if in fact we were going to say that LMD can provide an estimate of DNA quantity. You know, I know that there's a lot of issues with accreditation and DAB guidelines in terms of quantitation. And right now, you have to quantitate, you have to quantitate, you have to quantitate. As a researcher, for me, it's like, well, I don't see a reason, but I understand the reasons in terms of your guidelines. So we put this study in to kind of at least start the process of, if we're not going to use a traditional quantitation method in your lab, if you're not going to use a qPCR or one of these old methods like slot blot or something like that, you're going to have some data to support that you can make an estimate of DNA based on the number of cells you collect. So we did this study, and we collected cells by LMD. We actually used kind of two methods to quantitate, and I'll tell you, we used a QIAGEN protocol to extract these. The reason why is we found the Lysengo extraction protocol it inhibits qPCR. It doesn't seem to affect at all any kind of the Amplistar kits, but when it comes to qPCR, which with my discussions with other people, is a little more sensitive to inhibitors, we found it a problem. So the QIAMP protocol we used in this study. We used real-time qPCR to quantitate our samples, and then we kind of did a very loose quantitation by running those samples using Amplistar PISA Profiler Plus, and just kind of seeing the peak heights relative to standards of known amounts. And I'm going to also warn you too that second method that I used of relative amounts of STR-PCR, that's really just a kind of a general idea because we use low copy number work here, so we were amplifying a lot more than you normally would. So I don't know how accurate the second one is, but we kind of threw that in. So let's look at sperm first. So we collected all these different numbers of sperm, 300 down to 500. 300 down to 5 sperm. We also have the ABI positive control we use. We both quantitated that, and we did these all through the extraction procedure. So if we look at qPCR, that looks kind of grim, the yield. It's fairly consistent. You have from about as low as 12% up to about 23% yield. And you think, gosh, I'm only getting that much out of my sample. And like I said, this is the only study I've ever seen in any of the literature. So perhaps when you're doing your extraction, that is actually what your extraction efficiency may be. If we do it by the STR product, as I said before, and some of these I had off scale, so I couldn't put up there. It wasn't that much difference. I mean, we're in the 20s here, the low 20s%. And if you look and you think, okay, is it the LMD collection process or is it the extraction process? Am I losing cells? That's why we also use we use known quantities of DNA, and we extracted it through the QIAGEN process. And we still got fairly consistent to what we would on our estimated the amount on our sperm cells, this low amount of yield. And with the E cells, I just did qPCR on the E cells. On this study, for some reason, I got higher yields. And I can't explain that, but it was consistent. We got a certain amount of yield on the sperm cells percentage and a certain amount on the epithelial cells. But again, you're still losing at least 50% of what you expect. And why? You know, is it the extraction process? Is it the handling and the manipulation? Is it the nuclear material itself and how viable it is? I don't know. But the thing is, we did determine that it's low, but it was consistent. You can actually tag on, okay, this extraction method has a certain type of efficiency to it. So what does that mean? We can actually say, okay, I collected a certain number of cells, my extraction efficiency is X, and we can estimate the amount of DNA that's actually going into our PCR reaction. Now, this doesn't really make a whole lot of difference with low copy number anyhow, but it's just kind of interesting. And again, if you're thinking about actually saying, I don't need a quantitation method, and I'm just going to go right to PCR, at least you have some data behind it to saying there is an estimate of DNA that is going into the reaction. And the advantage is those quantitations that you're doing now, you can avoid. There's time consuming, and you can consume your sample, so you're not doing that anymore, and it's completely eliminated. Go ahead.
A couple comments about this, again, from a case working lab standpoint, because this is one standard, of course, that we've considered. We say, okay, because our goals with the LMD are not only to get this, physical separation that we can do and not have to do the whole differential, but of course another goal is how quickly can we do this? If we can actually skip the quantitation step and pretty much almost skip, any type of purification before that, we're speeding up this process quite a bit. Well, if you think about the quantitation again, when you're counting those cells, you are actually assessing the quantity. And again, just like Christine pointed out, with your extraction, even though you've done like a study of quantitation, there's so many variables in there, we don't even really know why you're losing the efficiency. Right. But another thing you have to keep in mind is when that standard was put into place, it was put into place back when D1S80, PMDQ alpha, where very large amounts of sample and sometimes the complete extraction volume was used to do the further downstream analysis. So what was happening was you were using up all your sample, and then let's say you had to go back or something, well, it's gone. So that standard was actually put into place very early on in the process of STR analysis. It's actually quite an old standard. So I think, to me, an argument can be made for a quantity is being assessed here. And to me, this is actually a better quantity assessment than QuantiBlot was, which we all used for so long. So to me, there's an argument that can be made here as far as that standard. Also, I think, just like when they wrote that standard, the technology was changing. I think the same thing's probably going to have to happen here. If LMD becomes a widely used tool in the forensic laboratory, I think that standard may have to be revisited.
Yeah, I mean, I totally agree with you, and I know how hard it is to change those standards.
Yeah.
But it's like anything else. It's like as the technology evolves, we really have to take a second look at some of these things that we're doing. All right. So we're going to move on to the meat of this whole thing, and that is the mixture study. So the first kind of mixture study we're looking at, let me see if I've got this right. Okay, so I'm kind of breaking it down in two parts. The first part is the mixture study with you collecting a lot of cells. Obviously, we collected a lot in the beginning, so we wanted to kind of make sure we had results. So we prepared mixtures. These are actually more difficult mixtures than the mixtures that you saw. This one is mixtures equivalent to half a female oral cotton swab and 1 microliter of semen. You guys were looking at 1 buccal swab with 5 microliters of semen. Kind of did that to just make things easier for you guys first time out. And we collected 75, 150, and 300 sperm cells. And the sperm cells were recovered from the mixtures, and PCR amplifications were performed using very standard Amplistar protocols at 28 cycles and 50 microliter reactions. But we also did what we called extended PCR. After we were done with the first PCR, we took out half of that product and we amplified it for another 6 cycles with more TAC. And that wasn't really to necessarily increase sensitivity at this point in the study, but we wanted to see if we could find that female fraction. We wanted to see if we could detect any contamination, and that's the reason why we did the extended part. So we analyzed both of those, both the 28 cycles on the CE and the additional 6 cycles on the CE. So this is just before any separation is done. DNA mixture, we just extracted the whole thing and ran it so to make sure we actually had a mixture. This is just one of the samples. And the female alleles are designated by the red asterisks, just so you can see that we in fact did this. And so here's an example of one of the samples. We collected 300 sperm cells and we ran it and we got just the sperm profile. And these peak heights, let me point out, right now early on in this study we were only getting from about 200 maybe 400 RFUs. This actually improved as we got more proficient with our techniques. So that 300 sperm, we're good. Okay, what about 150 sperm? Using standard PCR, we still got an entire male profile, which is very nice. And again, I'm sorry, there was no female carryover whatsoever seen. But if we look at the extended PCR, what are we still getting? Still the same, just male profile and no female carryover in those results. Oh, actually there was, let me see, I wrote down in here, in this particular example, there was one, that would occasionally happen. I think down here there's supposed to be, right here. There, you can see right here it missed it, missed the call. There should have been a real peak here high enough so that we didn't always have perfect data, but in general we would get nearly full profiles for 150 sperm cells. Okay, how about 75 sperm cells? And I put this in on purpose. This is some of our worst data because you don't always look up perfect data. And so you can see this looks kind of a mess. I didn't get very good results. I showed this just to show what extended PCR can do. Remember, this is the same exact sample. I just took an aliquot out and I amplified it longer. And then I got a full profile here. So what does this tell me? That, wow, this technique can really be used for low copy number work. But again, no female fraction detected in the sperm. So things are looking good. We've got down to 75 sperm cells. So where are we at on this? Okay, under how many, looking at all the samples we tested using standard conditions, 75 sperm cells, we detect partial profiles a lot of the time. With 150 sperm cells, most of the time we would get full profiles, 96%. And with 300 sperm cells, we'd always get full profile every time. And under extended cycles PCR, we'd get 100% of the profiles all the time. With all of these, we didn't see a single sample that had epithelial cell carryover. So then, oh yeah, and I put this into what about the peak balance, just to kind of throw that in. We calculated the heterozygote peak height ratio as the height of the lower peak divided by the height of the higher peak expressed as a percentage. And under standard PCR conditions, we were getting peak height ratios within acceptable ranges, around the 80% range. Under extended cycles, not surprisingly, we're losing a little bit, especially at the 75 sperm level of our peak height ratio. But it's still within, I think, acceptable ranges. 150 sperm cells, we got about 85% of a peak height ratio. And remember, what we're looking at here is and I think I heard Kelly talking about that yesterday in class, is that 300 sperm, what does that remember? That's about 1 nanogram of initial material. But the yield study, believe it or not, was after this. We didn't realize actually how much we were amplifying at the time. So it's not really 1 nanogram you're amplifying. It's actually much less. But that's what you at least start with. Okay. So in summary, for the mixture study, the first part of the mixture study, LMD separation of sperm cells from an epithelial cell mixture results in a single semen donor genotype. And the lower limit of detection using ABI user guide PCR protocols or standard conditions is somewhere in that 75 to 150 sperm cells. And when Kelly talks, she may have a different range. This isn't our study under our conditions. And I'll be actually interested to hear what her range is. They used a lot of different protocols than we did. But with extended cycle analysis, you can actually extend that detection. And that's what prompted us for the second study, is the low copy number study. So low copy number, or LCN, there's a lot of different definitions of what that is. Some people say it's kind of less than 100 picograms of DNA in the forensic world. Some people say it's just when you start losing your signal below your threshold. But we wanted to kind of look into this. And we had these mixtures. We actually used the same mixtures we did the first study. And we collected instead from 80 cells down to 5 sperm cells. And actually, I did do some tests of 2 sperm cells unsuccessfully. But most of our samples were from 80 to 5 sperm cells. And then we amplified those using Profiler Plus. And we used both 34 cycles, and we collected also samples at for 38 cycles. And again, these still are 50 microliter reactions. So first looking at the 80 sperm cells at 34 cycles, full sperm donor profile, and no epithelial cell carryover. This is good news so far. And then 40 sperm cells, the same story. You're starting to see some allelic imbalance. You look right here in amylogenin, quite a bit of imbalance, some a little bit here and here. This is not unexpected. Then 20 sperm cells at 34 cycles. Again, just the male profile was detected. Kind of the same story as the 40 sperm cells. And again, allelic imbalance. But still, a very nice, clean profile obtained. Then 10 sperm cells. This one actually is this is a full profile. We didn't always get a full profile with 10 sperm cells, but full profile with some peak imbalance, but very clean. And then I didn't have a separate one for 5. This is just kind of showing side-by-side comparisons of all from 80 down to 5 sperm cells. 5 sperm cells, we would get pretty much partial profiles, but they were very clear types. And what was nice too, and maybe it was our procedures, but we wouldn't get non-specific PCR product, which I know a lot of people get with low copy number work. We really didn't. We get very, very clean profiles. And I don't know if it's, I mean, remember, you think about laser microdissection, you're really just collecting this little sample as opposed around, say, the sperm head. If you have an entire extract from a swab that was collected at a crime scene, that who knows what kind of dust and other cellular debris floating around in there, maybe that's why people are getting more nonspecific product using more traditional methods. So it's something to think of. It's not just cleaning up, separating from your epithelial cells, but you might be just getting a cleaner sample because of that precise dissection. And those arrows, the red arrows, just indicate some allelic dropout. You will encounter that at that low level. Okay, and also I wrote down, you're wondering about the RFU heights, if it's difficult to see. So with 80 sperm cells, these are very high. They're actually almost blown out. So it's really on the edge of using that many cycles. We have like 4,300 RFUs. And the 5 cell samples, some are about 1,000 RFUs. The nice thing is that really, and I'll say most, all samples, there were no female carryover. And I say most. Okay, well, I'll say most and say in a couple slides I'll explain it. Here's just another slide talking about the percent of profiler plus profiler detected for the collected cells, kind of a summary of all the samples that we did. So with 80 cells, we always got all the entire profile. 40 cells, there were just, I think, a couple of dropped out samples that we saw. 20 still looks good with most of the profile detected. Really, when we get to 10 and 5 cells, that we have a significant drop in the number of alleles detected. But usable partial profiles. So remember, we did 34 cycles. What about 38 cycles? Does that improve any of these samples that were just 5 and 10 sperm cells? No, is really the short answer, is that at 38 cycles, we really didn't see a significant difference. I know it shows a little bit here, but there's no significant difference between using 34 or 38 cycles for 5 or 10 sperm cells. And in fact, with 38 cycles, we did observe a little more noise, I would say, in our PCR product. And just a little note here that you might want to write down. The RFU threshold we did for all of these samples was 50 RFU because we really wanted to see everything. We wanted to see even the contamination if it was there. With 80 cells, we always had RFUs above 200. With 40 cells, they were always above 100 RFUs. And with 20 cells, all but one allele we found above 100 RFUs. Just to give you kind of a feeling of the sense of what we were detecting. And so with this, this is the part that I said, oh, I'm going to get back to this. And that, did I ever detect any epithelial cell carryover? It only happened once in the entire 2-year project. But I think it's important to mention, we did have one single sample that consistently had epithelial cell carryover. So this is the 80 cell sample and the 40 cell sample, and the asterisks indicate the actual female alleles that were carried over into the sample. We were kind of wondering when we did this, was it a user that, it's a collection error? Should we go back and test it? So we actually went back to the same slide, collected the same thing, and really got almost the same exact results. So, okay, we still have contamination. Then we went back to the pellet, we re-smeared it, prepared it, and did this again. We didn't get a mixture. We got a nice clean profile. So actually, we kind of determined that we didn't really know why that particular sample on that particular slide consistently had carryover. Go ahead.
No, you said carryover or contamination. Like, was this the female type you expected?
Yes, I'm sorry. Yeah, it's the carryover. I'm sorry if I'm using the terminology back and forth. The mixture, it's the female alleles from the mixture.
Okay. So it wasn't something maybe coming from someone touching the
No,
slide?
no, it was consistent with a female that was part of the mixture. So we actually really don't know why this happened on this particular slide. As a researcher, I consider this an outlier because it was just one sample that ever happened in the big study. But it's something that maybe it will happen in forensic casework. I don't know. Some type of conditions were just right for this to happen. There's some theories about this. Even when you have differential extractions, sometimes even if you have tons of sperm and you wash, you still get a mixture, and you wonder, why am I getting a mixture still? And there's some theories about perhaps the exogenous DNA from the female that's floating around has kind of a binding affinity to the sperm. Something kind of be interesting for someone to continue doing research in that area, I think. So what was our summary of the low copy number mixture study. Minute numbers of sperm cells can be separated and recovered by LMD from epithelial cell mixtures. That's good news. And STR genotyping can be attained with as little as 5 sperm cells captured by LMD using that increased PCR cycles. And I was real happy with this, that we got very clean results and no non-specific product using low copy number work. And actually, I think at this point then we are ready for a break, and then we'll continue. Does anyone have any questions about this stuff that I've done so far? No comments? Yeah.
What type of, did you use the Lysengo when you did?
Yes.
Okay.
Yeah. This is, with the low copy number work, it worked perfectly. The same protocol you performed. The Lysengo in one tube, collection was in it, the extraction, and we add the PCR master mix directly to the tube. So that it never leaves that tube until you're ready for CE. Low copy number work, I think that's really important to do that. And, yeah. Okay. So let's take a 15-minute break or so, just a little after 10, we can come back.